We're going to continue on with clustering and classification and talk about one of the other major methods used in practice in industry, which are classification trees. So two of the dominant paradigm algorithms used in industry for supervised learning were support vector machines, the other one being a classification tree. Both are still commonly used, partly due to their success and their flexibility and also all the innovations you can build around them. All the details can be found here at the databook uw.com and all the lecture notes plus code, Python, MATLAB, and data. So I want to talk about classification trees, and in particular, it's an algorithm that's very straightforward to use. It's you're not solving some big optimization problem. You are scanning through your data, and so that is part of the cost of these, but it's a very effective tool, and I'm going to just tell you how it works. And also there's versions of it called random forest that I want to highlight, which is one of the important uses of it, especially as what you would like to do is build ensembles of these trees. Every time you split the data from a training set, it's unique to that training set, but if you do it over, just like cross-validation would, you do it over several draws of that data, you would get very different results. And so you would, not very different results, but especially as you start splitting, it would be different, but then you would maybe average over those to do a random forest and build an ensemble of models. Okay, so how does this work? It's actually pretty simple. So let's go back to the setup about supervised learning. What I give you in supervised learning is data and labels. Right? So the data set are some n-dimensional vectors, which are the features, the measurements you collect out of the system. And there's, let's say, m points, and each one of the points has n features, and each one has a label, +1, -1. So what we're going to do is we're going to take this vector, so the x of j here represents the jth data point, which has n components. And what we're going to do is we're going to scan through all n of its components across the entire data set. So I'm going to say component 1 of the vector, let's look at that, and let's actually look, if I just look at component 1, and I just try to associate component 1 with the label being +1 or -1, how well do I do? Okay? So if I just use that component to make a classification decision, how well do I do? And I do it for all n components. And so what I do is, as I scan through each component, I look at the one that did the best in classification of the data by itself. The one that did the best, that's where I design a split. In other words, in the second component, for instance here, could be that if I look along the second component, it's a very good division of dogs versus cats. So you would split right there. That's your first tree cut or first branch that happens in your decision-making process. So let me show you a simple example of this. And this is the iris data set that we've played along with before. So we have 4 features. The feature space, the measurements are 4-dimensional. The sepal width, sepal length, petal width, petal length. There they are, x1 through x4. So we have these 4 features. We have the measurements across the data set. We also have up to 3 labels. Right? We have Setosa, versicolor, virginica. Those are the 3 labels we have for this. So what you're going to do first is walk along the x1 direction. And so what I've drawn up here, this is what you're seeing over here is x1, x2, x3, x4. And what I'm going to do is just do a mental exercise. Let's go along the x1 direction and see how well does splitting in the x1 direction do in terms of separating the data. So here's the x1 direction. If I walk along here, notice it's very hard for me to cut anywhere in the x1 direction and get a very clear discrimination between the magenta, green, and blue balls. What about the x2 direction? Now come over here, scan in this direction, and again you see pretty hard to draw a line here that separates the magenta, green, and blue balls. That's about the x3 direction. If I scan along here, this is quite remarkable because in fact, I can completely separate the magenta balls from the rest of the data. So the x3 direction looks very promising. right? And in the X4 direction, again, I can scan this way. It also looks pretty promising, although it doesn't look quite as, look, the gap here in the X3 direction is a little bit bigger than the gap here in the X4 direction. So what it decides, it says, I will split here along my first split is in the X3 variable. I get a very nice separation between this class of magenta balls and the rest of the data. Okay, that's your first split. You've made a decision. Now, the way the splitting works is now you've said, okay, now I can take this data out of the picture because now I've basically said, okay, so I've got the split here. Now let's look to see what's going on over here with the rest of the data. Now let's go to a second split. Again, I can scan through the data and say, which direction gives me the best split? Again, I can look in these directions. The X1 and X2 don't give me much, but as I scan along the X3 direction, or sorry, the X4 direction here, notice if I go this way, I get a pretty nice split between the blue and the greens. So it makes a second split here. Now you walk along X3, split again. So you can split along a variable direction multiple times. But at each iteration step, you go down a branch now and you scan across the variables, decide if you're going to split again and again and again. Okay? Now, how many times you split? Well, that depends a bit on how many labels you have. Okay? So here, what we know is we have 3 labels. So we have 3 types of flowers, and so I'm going to do 3 splits to try to see, can I split in these feature directions in such a way that I give you the best discrimination between the 3 clusters of irises, okay? And so this is a nice picture because graphically you can see what the process is. And also that I'm just scanning through the data. The algorithm is a very simple scan through the data, and there's some if statement and for loops. So no high-end optimization here, just scan through data, which can be costly if it's very high dimensional, but it gives you a nice way to go about supervised splitting of the algorithm and generating a tree. In fact, for that iris data, here's what these trees look like, okay? So first of all, your first split was right here. X3 less than 2.35 or greater than 2.35, greater than or equal to 2.35. If it's less than 2.35, I'm labeling those setosas. Okay? In fact, let's go back here. Look at the value here. The value right there is 2.35. Okay, that's if you run the code, you'll find that split. You'll find that this here is the best separation point, 0.235. So that's what the first split was. And over here is setosa, and then you just leave everything else down this branch over here. So now you come down this branch. Now you have your second split. X4 is less than 1.75, greater than 1.75. Okay? So that was this split right here. Now we're not quite ready to classify yet because notice when we do a third split, these blue balls are going to be part of these blue balls. So the blue balls are going to be part of these 2 pieces here. The green's going to be in that square right here. Okay? So I split again, 1.75, anything greater than or equal to 1.75 is Virginica. And then if it's less than 1.75, I come down here to the third split, and at 4.95, I go to Versicolor or Virginica. So Virginica lives on these 2 balls, which was those 2 boxes. Versicolor's here, Setosa's over here. Notice that everything is a nice, simple, parallel cut in the data, okay? So that's a nice way to do it. There are other techniques, innovations around this which allow you to do other kind of cuts, but this is the standard way to think about the decision tree and the cutting. So that's the iris data, that's its decision tree. Pretty nice, right? Very interpretable. I mean, you can start looking at these. X3, remember, the interpretation being here that X3 is the petal width. So if the petal width, right, so that's, you can go back here and say, if the petal width is less than 2.35 inches or greater than 2.35 inches, I know that if it's less than 2.35 inches, it's a setosa, or I'm going to classify it as a setosa. So it's starting to give you very interesting information and interpretable information. So decision trees are actually really practical and important because oftentimes what they pull out for you is meaningful information that you can actually understand, interpret, and make decisions with. Okay? So that's why they were so commonly used, in addition to the fact that they're easy to execute and you can go to high dimensional data and do this very nicely. Okay, here's the dog versus cat example. Same kind of thing. We can split along the two major directions, X2 and X4. Those are principal components 2 and 4. And you can see here the first split is if you're less than this or greater than this, you're -1. You do another split, -1, 1. In other words, cats, dogs. So it gives you a nice decision tree to follow to make these kind of assessments of how to do this. So let me show you some code of how to do a decision tree. And here it is. I'm going to first, it's pretty simple actually. So I'm going to load the iris data that comes from MATLAB. I'm going to just fit tree. There it is. I give it the measurements. These are the 4 quantities X1 through X4, along with the species, which is the labels. So the training data, the label. I tell it the maximum number of splits, so you can decide how to do this. Here, maximum number of splits can be 3. Cross-validation on, fit tree, and then tree is what comes out. This is what I've called it. So I'm going to go fit this thing, I'm going to get a tree, and I can actually, what I just showed you for that tree was this view tree. That's it. So very simple to execute, implement. I can run this very quickly. We can also do this on the cat-dog data. And the cat-dog data, I did it actually on the full feature set of the V values. So here it goes, first 20 V components. So remember, we build the SVD. I'm going to project in the first 20 PCA modes, essentially. Take the training data. I got a training data with their labels, with the test. And I can just build a model here, MDL, fit the tree, training data with labels, maximum number of splits, 2, cross-validation on. So 2 splits because I just want to get out dog cats. You could keep splitting and see if you can refine this thing. You can get the class error, and you can also view that model, which I already showed you, class error. And then you can run your model now, and you can do predict, take new data in, predict using the model and the test data, and it's going to tell you how well you did on that test data. So very simple architectures for some very high-end supervised learning algorithms. SVM is very similar too, in the sense that these things are extremely fast and effective. So that's kind of the major idea of a tree. It's a very simple architecture to execute, right? Just walk through the data, walk through the features, start to deciding on splits, which direction is the best to split on, continue the tree down. So that's, and it gives you this very nice, robust way to do it. The other thing that you have out of these trees is there's some advanced features there that you can see in the code. If you look through the code that's online, you'll be able to actually get things, importance predictors. So it also gives you estimates, for instance, of which variables are most important for predicting outcomes. So for instance, there is a census data set in there that will tell you which one of the variables that they measure is most important for predicting the outcome of the classifications that you would have, and here they are. So, right, so, you know, capital gain, age, education, these kind of things are, in fact, gives you a score for each of them as a predictor, an indicator for the outcomes that they have. So these are kind of nice diagnostic tools, again, built right in to the classification tree architecture. Now, before I finish on this, I do want to mention one important thing, which is this idea of random forest, okay? So every time you do this with sort of either noisy data or very high dimensional data, whatever training data set you pull out to sort of build these trees with, the training set itself can actually dictate very different tree structures. If I randomly pulled a different training data set, I'd get very different decision trees. So this is a little bit problematic. In the last lecture, support vector machines, I showed you that if you cross-validate dog-cat data, you can get models that are amazing and models that are not very good, so you have to cross-validate. So random forest is, in some sense, an attempt to cross-validate. And the idea here is use ensembles of data. It's very much looking like a k-fold validation. You do random draws of the data to build different trees, and you use the average of those models or an ensemble of those models to actually do your prediction, right? So you don't rely on one training set which essentially produces its own bespoke classification tree, while another training set would produce a different classification tree. You average over all these, in some sense doing something a lot like a cross-validation trick, and this is what random forest is. So in other words, just use all these different trees together in an ensemble fashion, and that's where the random part of the forest comes in. So that's an important innovation because it helps give you a more convincing model and also a more robust model for accuracy and prediction quality. So those are the main concepts between decision trees. It's very easy to use, and again, it's one of the major tools out there for supervised learning, right? So you have SVM and decision trees as sort of your two pillars outside of neural networks that are out in the community that are still used quite a bit, and because they're effective, at least the decision trees are highly interpretable, and so and also just a very straightforward algorithm to implement. You can find more details here, databook.uw.com. All the lecture notes are here in a PDF format. Codebase, Python and MATLAB, as well as more lectures, and all the data used that we've been using for these lectures are all there. So go enjoy, play around with some decision trees.